Okay. Good morning, everybody, or good afternoon, depending on where you are. Again, my name is Mike Blateau, and I'm a senior consulting engineer here at Ansys, the Reliability Engineering Services division of Ansys. Today, we'll be discussing vibration, shock, and thermal mechanical considerations when designing electronics, specifically the PCB layout. Like I said, when you're designing a piece of electronics, you need to understand the environmental loads that will be affecting reliability. So we'll go over a quick example on vibration, a mechanical shock, and a thermomechanical loading. And I'll be doing this with some examples and also showing how you would solve some of these reliability issues through using an iterative process using our Ansys Sherlock tool. And then at the end, I'll also do an example of what I was talking about with the thermomechanical analysis. It's actually the overconstrained PCB issue that sometimes can arise due to bolting the chassis against a big chunk of metal that's unyielding, or maybe potting the board a certain way, which leads to issues that way. Before we can do that, though, we'll go over some quick background on vibration, shock, thermomechanical, and I'll quickly discuss the tools that we're going to use. Like I said, it's going to be the Ansys Sherlock tool. I also a little bit of Ansys Workbench in there, and like I said, we'll go over the examples. For quick background on the various environmental loads. Like I said, we're only going to do vibration, shock. There are other ones. Some people like to consider humidity. That's really hard to simulate. You can't really do it through FEA. I suppose you could look at the swelling of the parts due to humidity. There's some other things also, electrical stress, overstress, electrical overstress, ESD, that type of stuff. But we're going to be focusing on vibration, shock, and the thermomechanical. So why do we worry about vibration? Well, it's about right after temperature cycling. It's the next reason electronics fail. And it's a high cycle fatigue type failure. You'll see leads breaking. You'll see where the lead goes into the board, it cracking right there for like a through part. And the sources of this vibration can be from multiple areas. Typically, like a vehicle going over a rough surface, or cyclic loads, like engine control module mounted on the side of a motor control module mounted on the side of an electric motor. It's just turning, and it's going to see like a fixed amplitude, fixed frequency type of input that's exciting the board, causing those leads to vibrate a little bit, and eventually causing high cycle fatigue. The frequency ranges for those are anywhere between 1 and 500 hertz. You'll see in some of the frequencies go above that, but typically 500 hertz is the limit, and you'll see that in a lot of the test profiles. So, like I said, there's harmonic and random. Random is just like I said, automobiles over rough roads. There's other things that can cause random vibe, just daily usage, people moving it around, but that's it's random. You really can't define it. They do test profiles that are based on a PSD curve, trying to simulate it, but it is random vibe. We do our best guess on trying to simulate that. Harmonic is a lot easier. Like I said, it's a fixed frequency, fixed amplitude. Typically, when we test for that or do a simulation for that, we'll do a sweep through various frequencies and at various amplitudes. It's a lot easier to do. Mechanical shock, similar to vibration. It's like a subset of vibration. You can get more acting like vibration, especially when it's a low amplitude shock that's occurring over lots of cycles. Maybe similar to maybe a pneumatic actuation where it's just banging away, and it is a shock, but it's more in line with a harmonic event where it's hitting it at a fixed frequency. But we like to say if it's up to 10,000 cycles, it's a low cycle fatigue. Over 100,000 cycles, it's high cycle fatigue. So Yeah, shock events can generate high cycle fatigue failures, but that it's rare. And if we got to do simulation, we'll do those really high cycle fatigue mechanical shocks as if we'll treat them like a harmonic vibe as an input for FEA, because you can't really the low cycle fatigue and overstress events for shock. That's more of a probabilistic type analysis where you say, is there a probability of it failing, on every shock event? And you'll see if you're ever looking at cross sections and you want to determine if something is a low cycle fatigue due to a shock event, or if it's high cycle fatigue, you can tell by the way the failure looks. If you see pad cratering, where if we're looking at a BGA, for example, if you see pad cratering, that's a low cycle. That's an overstress event, likely due from a shock event. If you see cracks along the intermetallic, the brittle intermetallic layer between the solder joint and the pad, that's another indication of an overstress event. And of course, if the parts are cracked, that is an overstress in line with a shock event. The last thing we'll look at really quick is thermomechanical. Now, this is not the typical shear stress type thermomechanical that you associate with standard solder fatigue, where it's in plane mismatch of the CTE. This is board bending due to chassis influence or potting influence. And like I said, we've seen where potting can rip pins out of the board because somebody didn't do something right. Today I'm going to look at, I'll do a simple model. I'll just show a simple model where we take a board and we bolt it to a piece of aluminum, and then we run it through the simulation using the Sherlock tool. Really quick review of our Ansys Sherlock tool. It is a reliability physics of failure approach to electronics design analysis. You give it all give all your PCB fab data. It could be Gerber's, ODB++, or the IPC format. And bring those in. You can bring in the bill of materials. You define the PCB stack up, give it all its different layers, layer count. It'll automatically determine percent copper coverage on each layer. It'll predict the modulus of that PCB, and it'll also make up the moduli for all the components based on die size, lead style, and that type of stuff. And from there, you can run all these different analyses. You can do the thermal cycling, the solder fatigue. You do mechanical shock. You can do a modal analysis or natural frequency analysis, or you can do a harmonic vibe and the random vibe. But you can also use, if you don't have Sherlock, or you maybe don't want to use those internal Sherlock tools, Sherlock can also be used as a front end to any type of FEA engine. We use, of course, for Ansys, we're going to use Ansys Workbench. And I typically will build the PCB model in Sherlock. And if I have to do something else to it, I will export it or translate it. Automatically hit a button, it automatically open up and generate a Workbench model of the board, so you can do other FEAs type stuff to it. And I'll just show it. I'm going to do a natural frequency study. I'll do it first in Sherlock, then I'll show it in Ansys Workbench. So natural frequency, whenever we are going to do any type of vibration analysis, we'll always do a natural frequency analysis first. One, it's to check the model to make sure the mesh is correct, make sure all the contacts are interacting properly, and just to determine what the frequency response is of the board. From 9 times out of 10, if you know the natural frequency of your assembly, you can determine whether or not it's going to have issues in the field. If your natural frequency of the board is 100 hertz, and that's where most of your vibration is going to be occurring, chances are you're going to have a problem. If it's outside that, chances are pretty good that you're not going to have any issue. Like I was saying, most environmental vibrations are below 500 hertz. So if your board is well above that, chances are you're not going to see any vibration issues. There is exceptions. If you look at Mill Standard 810, the jet aircraft, it goes up to 2,000 hertz. So you got to be really careful at those higher frequencies and be mindful of that. And you can see this is just your mil standard 810 highway truck vibration exposure for random vibe, where it gives you the different PSD levels at the different frequencies for different orientation. Simple. We probably all mechanical engineers know what pretty much drives modal response. It's going to be your dimensions, material properties. There's the extra addition, which Sherlock accounts for, is the weight of all the parts. A lot of large, heavy parts on a board. If you could put a huge, heavy part in the middle of the board, it's going to lower the natural frequency. Typically, if you want to raise the natural frequency up, you can either, change the thickness, make the board smaller, add additional mounting points, and you can play around with that to try to get the natural frequency outside of your environment. So this is a quick example. I pulled this is a single board computer, pulled the fabrication files, brought it into Sherlock, generated the 3D model, and ran a modal analysis. I took at every mounting hole, I added an aluminum standoff. And we ran it through, and we can see that this board is relatively low. It's got some really large connectors on the one side. There's unsupported span right there. You could potentially see issues at around 146 hertz. Only if those are through-hole parts, so chances are them having issues is rare. But if you were to stick, like a QFN or something like that in that area, you could see issues with it. So wanted to show, hey, you can do the same in Ansys Workbench. Now, I did cheat a little bit. I did use Sherlock. I used the Ansys Sherlock to export it, or not export, but to bring it over into Ansys Workbench. And you can do the same thing. You can run the modal analysis that way. And the results are pretty much the same. You get around 130. The mesh is slightly different. You could do some mesh studies to see, where that planes out. But it's good enough. It gives us a general idea of where the first natural frequency is going to be, as well as the second. On the second natural frequency at around 200, that really tall, it's like a combo jack where you got the Ethernet over the USB type connector. That's things starting to sway a little bit at around 200 hertz. So you got to just do that. Also, bring in the chassis to see how that's going to influence things. With this one, this is a sheet metal box. If it lays there, it also has a standoff in the middle. And you can see that the bottom of that, depending on how it's supported, the bottom of that box could start vibrating. And if there's a standoff that's coming up and attaching to the middle of the PCB right in that area, it could cause problems because right now the first natural frequency is being driven by the chassis, which is at around 117 hertz. So, you can get an idea of, you may want to stiffen this box a little bit to get that up higher. So we'll just go through a vibration example. I'm going to do harmonic. It could be random, but harmonic's really easy to do. It runs a lot faster. Pulled it out of the IEC spec, 10 to, and they're all the same. They all pretty much go up to 500, except for your weird stuff like space launches and jet aircraft and that type of stuff. But 100, and it's just a sweep at a fixed G level. Now in Ansys Sherlock, you do have what's called a damping modifier, and it does kind of similar. It is similar to what your damping vibration is, where if you set it to 0.2, that simulates a rigid mount where you could imagine the board directly tied to the vibe head on like a vibration table. I'm going to set it to 1. That's going to be what it's like in a sheet metal enclosure. You got some damping from the sheet metal, and it accounts for that. So after I run it, the Sherlock tool will tell me what parts are going to have issues. And in this case, it's telling me I've got 2 large Ethernet transformers. They're not the jack doesn't have the transformer built in. There's 2 separate SOICs that are relatively high mass. They have a lead frame. Those leads, because of the high mass of the part and where it's located, those are vibrating enough where the tool is predicting you could have lead fatigue. There's also another part on the back side of the board close to standoff, which is now saying, hey, where that's located, there's a lot. You can see it. You can see it right over here on the picture on the left. That translates to the picture on the right, and that part's on the bottom side. It's in an area close to a standoff, and when you get close to a standoff, you can get really high strains. Leaded parts tend to do really well in strain areas, but if you move them a lot, the leads, and that's what the tool's telling me. It's telling me U20 it has a really high chance of failure given that vibration profile. How do we something like that? So the tool allows you to quickly iterate and make changes. I mean, you don't have to follow the exact design of that they gave you. You can do what if scenarios. So the first what if scenario that I did was, okay, let me add 2 mounting holes and get rid of that mounting hole close to that part. You know, I got 2 clear areas. Maybe I can change the chassis. I can add these mounting holes, and I can see, you know, is that going to change anything? And it does. It now says, hey, you still got a problem with U33 and U34. We knew that because those are high mass parts. And you can see that they're in an area, you know, it's with the green next to the red. We got some relatively large mass parts. They're stiffening the board locally, and it's only allowed to bend in that area to relieve that stress. So they're in an area that's flexing a lot, so they have some issues, and we got to solve that. But it does take care of that U20 issue that we saw earlier. Since these are Ethernet transformers, you really can't move them away from the connector that they're associated with. A dual stack RF Ethernet connector. So those coils, those transformers need to be close to that part. Solution, people do it all the time, is they will stake the parts down with an epoxy. You can also do this. You can also go into the tool and say, hey, I'm going to put adhesive around these parts. You can run it again, and now, hey, everything works great. So moving the mounting holes and adding the staking helped solve the issue. Of course, it will probably be a lot easier just to move the part. So you can just move U20. You saw earlier that on the other side of that mounting hole, there wasn't as high of a strain. You could just drag the part over, rerun the analysis, and now you can tell the layout guy, hey, can you just move U20 over to the other side of the mounting point? Hopefully you don't get a lot of pushback, but from what I can tell from this, the board is actually kind of clear in that area. There's not a lot of routing going on. These aren't high-speed parts. So, you know, it shouldn't be a big deal for them just to move that part over. Moving that part is a lot easier than putting additional mounting holes or changing your mounting holes. You don't have to worry about, you know, designing a new box. You don't have to worry about adding 2 mounting holes and deleting the one and all the routing associated with it. So it's easier probably just to move that part, and you can see, run it again, boom, everything checks out. Just the quick takeaways. You know, strain sensitive parts. I mean, if that was a QFN in that area, it would have failed even quicker. QFNs, BGAs, your ceramic caps, they're all strain sensitive. They have issues in high strain areas, so you just got to be mindful of that. You have high strain areas, you're going to be near your mount points. Anywhere there's a large part and another large part, that gap between them, that could be a high strain area. So you just got to be mindful of that and how you lay out your big parts, because you can get, it's like a hinge effect where you get the localized stiffening, and then that board, as that board bows down, all that area where those parts are, so it just bows into the seam in between, and you get like a really high strain. So if you put a QFN in that area, or a BGA, or a ceramic cap, you could see issues. Pictures are always helpful on what a strain sensitive. As you can see, gull wings are and C-bend lead type devices. That lead acts as a spring, and you can see I just did a quick vibration displacement plot of some memory chips and a BGA, and you can see those gull wings that take up a lot of the motion of, and they act as a spring to protect the solder joint, essentially. You don't get that spring with without a lead frame. So you just got to be careful with these strain-sensitive parts, your QFNs, your BGAs, your ceramic chip capacitors, and that type of stuff. And that kind of leads into the shock, what we call mechanical shock. Quick definition of what a shock is: something stops suddenly, boom, it's a shock. In electronics, we kind of narrow it down. We say it's anything at least 10 Gs with a duration less than 20 milliseconds. Anything over that, it doesn't really do much. 10 Gs seems to be the limit. And we like to say it occurs less than 100,000 times. Like I said, if it occurs more than 100,000 times, it's a whole different failure regime. It's a high cycle fatigue regime. Personally, I treat that as a harmonic vibe. I put the G level in a harmonic vibe and do the frequency that way. Typically, like I said, we think drop as predominantly for mechanical shock. This is just a quick table where you can relate different heights. So if you know it's going to be dropped from 3 feet, you can get the equivalent shock you would need to do your FEA. So because a lot of times I'll tell you, I'm just going to drop it 3 feet on concrete. Okay, I need some way of relating that to a simulation. How would I simulate that? Easily, anyways. I mean, you can do it as a full transient where you take the board or take your product and drop it and do it that way, or you do the quick way where you just put those impulse inputs right on the mounting points and do the shock that way. And this is how you would. This is just for small stuff, the equivalence of a drop height and the G and duration of the shock that you would need to do. Like I said, people tend to focus mostly saying it's drop, but there's other inputs. There's the assembly process where you can get shock inputs. I've seen this happen multiple times. Predominantly deep paneling. Now, for deep paneling, actually sawing is pretty good. This picture shows it sawing, but lots of time with like a V-score routes, people will cheat and they will just stick the whole edge of the board in a groove and just bend it over and break it. And that's big shock pulse. We've seen joints pop because of that. Another issue I've seen is ICT test fixtures. They'll put the lid down and then somebody will have decided that they didn't need all the support pins on the opposite side, so the board actually has a lot of bow to it, and then they pop that lid off really quick and the board snaps up. And that's kind of similar to a shock event. Then there's also the big heat sinks. People will put those on and those will spring the board a little bit, and that can also be considered a shock event. So you just got to be mindful that there's other things besides drop that could be considered as a shock. But when you're designing for shock, the rule of thumb is a 3x of the shock pulse frequency. And the shock pulse frequency is where you take the duration of the shock, and it's essentially just 1/2t. The duration since it's a half sign, you got to times it by 2 and reciprocate, and that gives you your shock pulse frequency. So like a 10 millisecond pulse is a 50 hertz shock pulse frequency. And the rule of thumb is you want to be 3x that. So for your board, if you know it's a 10 millisecond, if you know it's going to be 10 G or 100 Gs at 10 milliseconds, you're going to want your natural frequency of your board to be at least 150 hertz. If it's any lower than that, you can get what's called a shock amplification effect, where since the board initially does that initial deformation and then resonates at natural frequency, it will actually amplify the damage. So you got to be careful. So you want at least a 3x of the shock pulse frequency for the natural frequency. That's why it's important to know your modal response of your board. Some of the ways you can mitigate shock, isolators, they now have these what they call the soft termination capacitors. If you have your ceramic capacitors are failing, we've seen that with a lot during assembly. Sometimes they'll blow the board a lot to try to fit the board in to get it to fit into the assembly, and they'll crack the caps. There's ways of part selection to solve that issue. That's a little more costly, but you can get what's called a soft termination. They have a soft pliable layer between the ceramic and the end cap, and it allows the capacitor to take in more flexing. And you can also fix it by bonding and that type of stuff. And like I said before, adjusting the natural frequency of the board response, by changing the thickness or the mounting points. Really quick shock example, just one BGA. You'll see this in a lot of cell phone guys use this a lot, where they'll edge bond to fix the issue. You'll see a lot of edge bonding to fix to protect against shock. So when you run a shock analysis in Sherlock, it doesn't give you time to failure. It gives you probability per cycle of a failure event occurring. So right now it's saying I've got about a 1% chance of failure per drop event, which is actually pretty high. If the product gets dropped 100 times over its lifespan, over maybe 5-10 years, there is a good chance that one of those events would cause something to fail. So how do we fix it? And like I said, we corner stake or edge bond. And we can add the edge bond. You can enter those material properties of the edge bond material in the material manager inside Ansys Sherlock. You can put those little potting tool, but you can put those little adhesive sticks around the part. You can rerun your analysis again. And what it does is it moves those strains out from the corners of the package. And now it's near zero. Chances are now we're not going to see a failure from drop or this BGA in particular. It's pretty much same guidelines for shock. Just be careful where you put your parts. There is got to consider other potential inputs for shock. It's not just drop. There's the assembly. There's the unmating and mating of large connectors. Saw that in the past where they were failing. The boards were getting damaged, and we didn't know why. And it ended up during tests, they would put the board down on a test board, and when they pulled it up is when they were actually breaking it. It was the unmating of the connector. It was a really large board-to-board connector with a lot of pins, a lot of force, and they were very careful pushing it down because they wanted to make sure everything was even as far as force goes. But when they were pulling it up, they didn't make the same consideration. So the board actually was failing after they unmated it, where it would snap and cause the BGA balls to break. Okay, so we're all familiar, well, maybe not, I don't know, but we're all familiar with the standard solder fatigue calculations most people do for parts. It's typically just in-plane shear. It's a CT mismatch type calculation. You take the properties of the board, you take the property of the package, you get the difference of the CT difference and the strain that it causes, and from there you can determine the solder fatigue, the cycles to failure due to temperature cycling. However, that doesn't account for these localized effects that you could see, especially when you bolted your board down to a large chunk of aluminum. We see this a lot in automobile modules where it's a cast aluminum housing, two halves. There's a board sandwiched in between it, and the board, those two housings are just cranked really tight against the board, and the board kind of has to go with where the aluminum tells it to go. And sometimes you'll see on the cold side, as that shrinks down, or even on the hot side, it buckles the board, and you'll see that buckling, and that buckling doesn't count for when you're doing your standard solder fatigue determinations, or cycles to failure. So you have to account for it somehow. Unfortunately, the tools don't have that in there, so we do it as a separate analysis. So I made just a quick example of a kind of like an automobile module. It's two halves, two aluminum halves, and they're going to be sandwiching a board together. Just made a simple. Got my 4 memory chips. I've got my CPU. I just stuck them up in the corner. What you need to do for when you're doing this type of analysis, what we're going to do is a strain versus strain comparison. So we'll run the board the temperature cycle, without chassis first. And from there, we'll get the leads. I strain with the board just totally free to move with the temperature. So these strains are really from the board and keeping the part. Baseline strains. And I do this in Sherlock. And then in you can still hear me, right?
The start of this slide. Yeah.
All right. So we've added the chassis back in, and we've run it again, and we can see now that the lead strains have doubled. So now we need to account for that in the solder fatigue life prediction that Sherlock gave us when we ran it. Now, this is really harsh oven cycle that a lot of automotive guys use. It's I think minus 40 to 100. One particular, most BGAs are going to have issues with that, especially if they're large. So these are numbers that we would typically see with that type of thermal cycle environment. However, if my baseline is 398 cycles to failure, which is the time to 63.2% failure, when I use Kaufman-Manson to adjust that based on the strains of the between the two conditions, you can see that it's going to drop it to 139 cycles, so about a third. So you can say with chassis influences, it's going to drop my reliability of my product. So you just got to be, this is a way we can estimate the influence of how you mount your PCB inside your chassis. You're not going to see this so much with a plastic housing because plastic has a lower modulus, but you can start seeing issues with your milled machined metal housings where if you really lock that board against that piece of metal. You can also see it when you bond a PCB directly to a piece of aluminum for like a heat spreader. Sometimes what people do, you'll have the metal in a certain area, they'll free up some other area where there is no metal, and then all the strains just get focused right on that free area because that's the only place the board can relieve itself. That didn't sound good. Same issues though, really, you just like if you saw that where I put those parts, it was kind of a bad spot to put them because I put them right near the edge where that board is being mounted against the chassis. So yeah, move those parts away. Yeah, keep those parts away from the high strain areas, and chances are you'll be okay. You just got to be mindful. But we do see people put these strain sensitive parts close to mounting points. You just got to be aware of it. You all have to be, like I said, and you'd be amazed how many issues we see because of potting. Potting, when it comes to board influence, we see so many problems with potting and potting done wrong or poor selection of potting as far as the glass transition temperature and its expansion rate. If you lock your board down into the bottom of a metal housing with a lot of mount points in that housing, and then you pour potting underneath of it, and then you temperature cycle it, that potting is just going to, the hydrostatic pressure on that board, because that potting can't expand freely, it's just going to bow that board and cause all sorts of problems.